Hi there. Now that we are done learning what an ellipse is, its parts, it's time to derive its equation. But first, let's recall some key concepts in ellipse. So to start, let's move this up here first. And so we start by recalling the definition of an ellipse. So given 2 points, say P1 and P2, and we obtain the distance from one of the point to the both focuses, or rather the foci. So we'll have this one, and we add them up. And we do the same for the other point. So we'll have this. By definition of an ellipse, we know that the sum of the distances to two fixed points of any arbitrary point in an ellipse must all be same or constant. So we have this two to be equal. To be more exact, if we choose the second point to be out here, so we'll have this, and we obtain its distance P1, or rather P2F1 and P2F2, like that. There. So if we solve for this one, so to solve this, we recall that we know that the length of the semi-major axis is given by A, and the length of the focal distance, or the distance from the center to one of the focus, the one of the foci, is given by C. So given that, we can obtain the values out here. So for the line segment P2F1, this one, to obtain this, we simply add C and A. Since when we add C and A out here, we'll obtain this whole length out here. So we'll have A plus C. For P2F2, what we do is we simply subtract A. So A out here by C. So by subtracting A and C out here, we'll obtain this. So we have A minus C out here. And then simplifying this, we can cancel out the C's since we have positive and negative C. And we'll be left with A plus A, or 2A. And so in general, that is how it works. The sum of the distances from one point to the first focus and the second focus, its sum is equal to 2A, or the whole major axis. So that is true in general, so take note of that one, and we'll be using that later on in our derivation. After this, we take note that we also learned in the previous video that the length out here, or half of it, this one, the length of the focal distance in terms of A and B, is equal to the square root of A squared minus B squared, wherein A is the major axis, or the semi-major axis rather, while B refers to the length of the semi-minor axis, this one. So take note of that one. So we'll be using this result and this result, as well as this illustration, in our derivation. So let's clear out some stuff that we don't need. Move these two up, this and this, and let's rearrange this one. So let's resize this, move this out here, and this. So that will be like this. And yeah, so let's start our derivation process. Let's first consider the case wherein the center out here, the center of the ellipse, is at the origin, or at the point 0, 0. So this will work for, the derivation would work for any center, but to simplify how it looks in our proof, or our derivation, we'll be considering the center at 0, 0. So if this one is 0, 0, then this one is length C, it follows that F1 must be the point negative c, 0. Similarly, since this one is the origin and this one is the point f2 with length c out here, then this point f2 must be equal to the point c0. And lastly, let's denote this arbitrary point to be the point xy. So we'll be using these 3 points in this derivation. And another thing that we need to remember is that if we recall the distance formula given 2 points, this is given by the square root of x sub 2 minus x sub 1 squared plus the quantity y2 minus y1 squared. X sub 2 minus x1 out here just refers to the difference of the x coordinates, while the y sub 2 minus y sub 1 out here refers to the difference of the y coordinates. And so, what we'll be doing is we'll be applying this distance formula to obtain the length of P1F1 and P1F2 equals 2. So that is, we'll be focusing on the equation out here. So let's first obtain P1F1 out here. To obtain P1F1, we'll apply the distance formula on this point xy and F1, which is negative C0. So that is, we'll obtain the square root of the quantity x minus negative c squared plus quantity y minus 0 squared. Again, this refers to the segment P1F1 plus applying the distance formula again, this time for this one and this one. We'll obtain the square root of quantity x minus c squared plus quantity y minus 0 squared. This refers to P1F2, the segment P1F2, and again, don't forget the equals 2a out here. So we'll have this. And so this will be our working equation. So let's clear out some things that we don't need anymore and move this out here. So resize that one and move this up here. There. And so this will be our starting point in our equation. Our goal here is to find an equation wherein what will be left is x and y, the arbitrary values, and a and b, since a and b are usually given in an ellipse, or that is the length of the semi-major axis and the semi-minor axis. So we'll be left with x, y, and a and b there. So just a disclaimer, the derivation for this one is quite tedious. It requires a lot of squaring, square root, cancellations, and such. So just bear with me and I'll try my best to explain this in the simplest manner possible. And so let's start. So let's start by noting that this out here, x minus negative c is equal to x plus c. Then the y minus 0 squared out here is simply equal to y squared. Similar for this other one, we'll only have y squared. So we have this. And from here, when we are given two radicals, the usual strategy is to isolate one first and then square both sides. So we'll be doing that. So let's move this radical to the right to obtain this one out here. And then let's take these square both sides. So on the left, we'll have x plus c, quantity x plus c squared plus y squared. So technically, we just remove the radical signs. Radical sign. Then for this one, we'll apply square of the binomial. So we'll have 4a squared for the square of the first term. Then 2 times the first and the second term to obtain this. And the square of the last term, which is this one. From here, let's expand these out here. So by square of binomial again, we'll have this x squared plus 2cx plus c squared, and on the right we'll have x squared minus 2cx plus c squared. Then from here, observe that we have similar terms on the left and the right. Oh, not really this, but this one, x squared and x squared. So we can subtract x squared both sides, as well as c squared, and as well as y squared. So these would cancel out and we'll be left with this, and let's compress this one. So we have 2cx equals 4a squared minus 4a times the square root of x minus c squared plus y squared minus 2cx. So this is what we have so far. And let's clear out some space and move this up here. Now, to solve this, again, what we want is to eliminate the radical, which is this one. And since this one is the only one radical left, what we do is we isolate that one on one side. So that is, we'll be moving 4a squared and negative 2cx to the left. So we'll have 4cx minus 4a squared equals negative 4a times the radical. Take note that we obtain 4cx out here since we move negative 2cx to the left. So we'll have positive 2cx, then add these two up and we'll obtain this. So I hope that one is clear. And then from here, observe that there is a common factor out here of 4 or negative 4. So this is just by some manipulation. And then that means that we can divide negative 4 in every side of the equation. So these would cancel out and we'll be left with a squared minus cx equals a times the square root of x minus c squared plus y squared. So I think that part is quite confusing, but I hope you got that one. If you have any questions, you can comment it down below and I'll try my best to explain what happened out there. Okay, good. So let's continue. And from here, what we do is we square both sides. So applying square of the binomial on the left side of the equation, we'll obtain a raised to 4 minus 2a squared cx plus c squared x squared. And on the right, so we just distribute this one here and then this one. So we'll have a squared, and then for this one, the radical sign will just cancel out. So we'll obtain this. From here, we'll just expand x minus c squared out here, again square of the binomial to obtain this. And then, so let's clear out some space first. There. Move this up, and I promise this one is the last part. So let's just continue. And then take note that what we do next is we distribute a squared out here. So we'll have this to obtain, this one out here. So a squared x squared minus 2a squared cx plus a squared c squared plus a squared y squared. And then from here, observe that we have 2a squared cx, negative 2a squared cx rather, on both sides of the equation. So we can, this is a typo. This one should be add out here. So adding that up, and then that would cancel, and then we'll be left with this. So let's compress this one. And then what we do here next is we try to combine the like terms. So that is, what we'll do is we'll be moving a raised to 4 to the right and a squared x squared and a squared y squared to the left. So we'll have c squared x squared minus a squared x squared minus a squared y squared equals a squared c squared minus a raised to 4. So a lot of squared out here. And then what we do is we factor out the term x squared in these two, and the term a squared or the factor a squared in this one to obtain this. So x squared out here is factored out and a squared out here is factored. From this one, we can divide a squared times c squared minus a squared both sides to make this one, the right side, to be equal to 1. And take note that we can do that since we know that a squared is not equal to 0. Since if it is equal to 0, it follows that a must be 0, but we know that to be not true since a out here has a length. And likewise, c squared minus a squared is also not equal to 0, since if it is equal to 0, then we'll have c squared equals a squared. But we know that to be not true since clearly a is larger than c. And so we can clearly divide this factor out here. So we'll have cancellations out here, and we'll be left with x squared over a squared minus y squared over c squared minus a squared equals 1. And we are close to what we want. What we next do is take note that c squared minus a squared out here has a value that we can obtain. Since we are given earlier, we know the value of the focal distance, this one, if we square both sides, we'll have c squared equals a squared minus b squared. And if we move a squared to the left, we'll have c squared minus a squared equals negative b squared. This means that this out here is equal to negative b squared. Since we have negative and negative out here, that just simplifies to positive. And so we have x squared over a squared plus y squared over b squared equals 1. Observe that this is what we want, since the values left are x and y are arbitrary values, as well as a and b, which is the usually given values in ellipse. And so we conclude that this out here is the equation of an ellipse. More specifically, an ellipse that is oriented horizontally centered at the origin. So to summarize what we had, to summarize this, given an ellipse centered at the origin, and given its semi-major axis and semi-minor axis, the length, then the equation of this one is simply given by x squared over a squared plus y squared over b squared equals 1. So take note of this one, but take note that this only apply to horizontally oriented ellipse centered at the origin or at point 0, 0. What about if it isn't centered at the origin? Say we have this one out here. Suppose this one is centered at the point hk. What would the equation of an ellipse look like? Although we didn't derive it by similar process, it's just even more tedious and problematic, and it's kind of hard to understand, but you'll see, and you may try that one on your own, that the equation for this one is equal to quantity x minus h squared over a squared plus quantity y minus k squared over b squared equals 1. So there's an additional minus h out here and minus k. So take note of this equation. And lastly, or last case, what if we have an ellipse that is oriented vertically? Well, you may try as an exercise that the equation of an ellipse oriented vertically is given by the quantity x minus h squared over b squared plus the quantity y minus k squared over a squared equals 1. So essentially what happened is that b and a out here flipped or switched places. Since in a vertically oriented ellipse, the semi-major axis is along the y-axis while the semi-minor axis is along the x-axis. So if you want to try this one out, I suggest you can try it first on the point 0, 0 or on the origin as well, since it is much simpler to do. And so again, the two equations that you need to remember is this one for the equation of an ellipse oriented horizontally, and this one for an equation of ellipse that is oriented vertically. And so these two are the equation of the ellipse. So write this one on your notes, as this one is what we'll be using and applying in the next videos when we try to answer some examples and exercises on the ellipse. So yeah, I hope you enjoyed and learned a lot from this one. It's quite a lengthy video since the derivation process is very technical and very tedious, but it's satisfying once we are done. So yeah, that's it, and that's all for this video.